Okay, I would like to spend today's time, depending on your interests. So I could started my, hold on, I should tell you the next topic I'm going to talk about. Right now, I'm actually talking about more of a some of the operating system issue, which is beyond the traditional way of looking at operating system. I want to basically just tell you what I'm going to teach next. The slide number 4, which is the SCOSC, social-centric operating system kernel, which I actually developed this project for a long time. This is a project called David Social Link. I started working on that, and essentially around the time when all the social media being started. So I can actually start with this topic. On the other hand, I can actually be happy to start this after your second midterm. But this will go for a few lectures, at least 2 lectures. I try to be moving fast, so you kind of not dragging too much about the detail, but then you can get an idea about what's going on. All right, so that's one thing we can do. And the other thing which we can do, happy to do that, is we can spend today in the lecture for answering any question or go over some of the simple exam question, because I think you guys must feel panic that you know what, this is a video I share with all my students this morning. Maybe I will play like a few minutes to tell you that. Let me actually play a little video. I actually show this, have a great discussion. Wait a minute, why can I come out? And show. Remote student, you can see my screen, right?
Yes, Professor.
Yeah, okay. I'm going to show a video. I hope you can see the sound. Wait a minute. Does this has a sound? Okay, good. It does have a sound. So I'm going to plug it in. Let's see if it works. Let me tell you which video I show. And this is one of my favorite video, by the way. Just the purpose has very little to do with operating system, but it has every reason for every student that you should actually know this. It's a different way of looking at this. This is by Roger Bregman. He is considered by Guardian one of the most influential young thinker in Europe. I don't want to show this version. This version is actually not as good as the other version. Hold on one second. I'm actually going to copy and paste. If you've never taken the ethics course, you might have missed a lot of good stuff. Wait a minute, is this the one? Okay, sure. Remote student, can you hear me? Can you hear the sound?
No, Professor.
Can you hear it now? I'd like to start with the sound. Okay, good. How do I get rid of this? I want to get rid of this. Sorry.
Why do the poor make so many poor decisions? I know it's a harsh question, but take a look at the data. The poor borrow more, save less, smoke more, exercise less, drink more, and eat less healthily. Why? Well, the standard explanation was once summed up by the British Prime Minister Margaret Thatcher, and she called poverty a personality defect. A lack of character, basically. Now, I'm sure not many of you would be so blunt. But the idea that there's something wrong with the poor themselves is not restricted to Mrs. Thatcher. Some of you may believe that the poor should be held responsible for their own mistakes, and others may argue that we should help them to make better decisions. But the underlying assumption is the same. There's something wrong with that. If we could just change them, if we could just teach them how to live their lives, if they would only listen. And to be honest, this was what I thought for a long time. It was only a few years ago that I discovered that everything I thought I knew about poverty was wrong. It all started when I accidentally stumbled upon a paper by a few American psychologists. They had traveled 8,000 miles all the way to India for a fascinating study. And it was an experiment with sugarcane farmers. You should know that these farmers collect about 60% of their annual income all at once, right after the harvest. And this means that they're relatively poor one part of the year and rich the other. And the researchers asked them to do an IQ test before and after the harvest. What they subsequently discovered completely blew my mind. The farmers scored much worse on the test before the harvest. The effects of living in poverty, it turns out, correspond to losing 14 points of IQ. Now, to give you an idea, let's compare.
Okay, I only want to show until this point. So if you apply the concept of you became harvest under poverty or under a lot of pressure to take an exam, you lost 14 of your IQ point, okay? So just relax, okay? Education, sometimes we kind of give you pressure for you to go into an exam. I really want you to try to get away from that, all right? Relax, enjoy your life, and just, you might actually do much better, all right? That's why, I mean, the rest of the video is amazing to talk about a concept called utopia and talk about what they call universal base income, which means that everybody will guarantee universal base income. Everybody work for 15 hours per week. And also there's no border between any country. That's basically his book title in this talk. It's amazing. There's a lot of thinker I got to enjoy when I teach ethics. This and many other actually influence a lot when I doing research on ethics. I emphasize, some of you might heard I use the word autonomous thinking. So human being need to be autonomous thinking instead of being influenced by what kind of pressure we're going to make a mistake, something like that. Something to just cheer you up, okay? Even though I know I'm going to give you a really hard test on Thursday, all right? No, I'm just kidding. All right, so having said that, what should we actually spend today to look at the exam question, some of the past exam? Let me ask. Okay, let me actually unshare my screen. Okay, so are there any particular question you would like to address? Otherwise, I will go through some of the question. I actually just gave it to you today, about like 30 minutes ago.
Oh, I have one like general question.
Please go
Not
ahead.
general, but can you tell me like what parts of the lecture or what I should study so that I can be prepared for the test? I think the past problem for sure, but
Okay.
do you have anything else?
Okay, so there are 5, I think there are totally 6 papers you should study. So let me share my screen to tell you what are those 6 papers, okay? so those are being, let me kill this one. Okay, so I'm going to the announcement. I actually have a little 6 paper in the announcement. So the first paper I gave out was, wait a minute, where are those 5 papers? Hold on. Huh. I thought I gave you all 5, 6 paper. Scroll up. Here. Okay. Thank you very much. I'm getting there in terms of my years of forgetting everything. So this is the 5 paper. You can see the first paper is our network file system. The second paper is AFS, but I actually replaced that paper with another one, which is, I think is better. And then this is just Wikipedia for 2-phase commit and 3-phase commit. And then the last one, it talks about the GFS, Google File System. So those are essentially those 5 papers. And then I gave a better paper in this particular message. This one I think is a better, much more readable paper about Andrew file system. And I actually gave the 6th paper is in PCP. Where's the PCP paper? This one, yeah, okay, thank you. This one is the paper of PCP. So that's regarding the reading for you to see what's going on. And then this one plus the PowerPoint slides I share, and also the how do I say that, with my recorded video, you can probably see which slide I cover and which topic I cover. So I will only ask you questions related to those parts that's actually covered in my lecture. Okay, does that address your question?
Yes, thank you.
You're welcome.
Professor, question.
Sure.
Can you go over the format of the second midterm one more time?
It will be exactly the same format like the first midterm. Does that answer your question, or?
Yes, thank you.
Okay. It will be exactly the same. Okay. Any other question? Yes, please. No, I will not ask question about VNO. Yeah, I have a lot of stuff already to cover. You know, it's like the first midterm. It's like there's a lot of topic. I can only pick some to just check it out for you to make sure you understand something. Yeah.
How many questions do we have?
2. We still have 2 questions. One, just like last time. One question might have 2 parts, just like last time, the first 2 parts of what is really last time, first 2 are the same question. And then one question based on some, like you should know, like a test your knowledge. The second question will be more application, will be a bit of open-ended, this kind of question. Yeah. Yes, please. Which paper? No, sorry, I actually missed. Oh, sure. Which one? Is there a particular one you would like to go over?
Which one would be relevant to this test? Because you did publish a few.
Sure, I will, because I actually just provide like a 4 or 5, right? Let me actually go over that right now. For each of the question, I can actually tell you that's covered, that's not covered.
Do you need to go over the monthly published for midterm one? Or not the monthly?
Yeah, okay, we can do that as well. Because some of them are also related. Some of them are actually duplicate. Okay, so that's a good point. Thank you. So that's what I'm going to do right now. Let's go to the simple test I gave today. Let's look at the first one.
Oh, sorry, before you start, may I ask another question?
Go ahead.
I went over the PCP course, and I noticed that there's a lot of things that needs to clarify. So may I know if there's some time that could allow us to ask questions regarding to PCP?
Yeah, today we have office hour at 4 o'clock.
Okay.
And tomorrow we'll also have office hour at 4 o'clock. So today and tomorrow you can ask questions about any specific question. But PCP is something which is I can actually, if we have time today, I can go over some example to go into that as well. Okay. I know it's for first time if you never get exposed to the idea of PCP, it could be a bit tricky for you to catch that. Okay. All right. So this one was a winter 2013 final. This one is about transaction, is optimistic concurrency control. But I said we're not going to do optimistic concurrency control, so you can skip that. And this question is a standard two-phase commit. This particular part will be covered. Okay. So let's look at this question. You see that this question is saying that under exactly which condition under two-phase commit protocol, we have to wait for a crash server to recover before we can continue. So that is actually the most important question, in my opinion, in understanding two-phase commit and three-phase commit. Why we need three-phase commit? Because of this particular condition. So let me first tell you the answer, and then we can actually discuss a little bit about the rationale. The exact condition for that behavior is that all the good server are in wait state. All the good server are in wait state. And there is at least one server crash. And the coordinator also crashed. Okay, so that's the exact condition. All the good server, they are all in wait state. And then there was one server which is actually crashed. So we don't know its state. And we don't know the coordinator or the client who also crashed. Okay, in that case, that is the only condition that we don't know how to move forward. If you remember my lecture, the other condition, we have a way to resolve, but this is exactly the condition we get stuck. Okay, so that's the question we try to ask. Okay. Should I go further? Yeah.
Can you review like that other condition and how you solve it?
Okay, sure. Sure. Let me bring my slide. So the answer to this is on this particular slide. Let me see, where's the slide? Here. See, these are the 4 different conditions. That the condition I was referring to about a minute ago is condition 1, the second condition. All right, so we can look at other conditions. The first condition is some server have not received the vote request. So if that's the case, then essentially you just abort. You can just abort, right? Because you haven't even started to vote, so you can abort. Okay, so the third condition is that if some of the server already in abort or commit state, then that's clear. We should just, if there's a one server that's already in abort, sorry, they must be, okay, I take it back. Condition, the third condition or condition number 2, I'm sorry, I'm computer science C programmer, always start with 0. And if some server are in abort or commit state, that's actually where it's impossible to have both some server in commit and some server in abort simultaneously. It should be, if the protocol run correctly, they should all be unison. So therefore, in this case, if it's abort, then it's abort. If it's a commit, it's a commit. Okay, that's, and the fourth case is the same thing, right? If all of them are commit or abort state, of course, you go for abort. Yeah. Yes, that's right. Yeah, you need to have a, yeah, coordinate. Well, the thing is this. Yes, you need to coordinate it, but there is a tricky part about the third case is that there are servers who are crashed right now. So when they, because they already received the message commit, so we, depending on that server, have the capability, like some update or like this kind of journaling, they will actually be able to recover that commit and then continue to do that. So we're counting on that condition. If the server doesn't have that capability, we might need to initiate another instance of the server. Or we can actually, in this case, sorry, I know what I want to say. Because we cannot wait on that machine to recover because we need to move forward. So we have to really like another copy server to replace that. And this time we say you have to go for commit because others already commit. So you have to just commit. That kind of corner case, you have to be careful. That might be application dependent. Some application it will be okay, some application it's not okay. Yeah. Okay. All right, let me go back to the question. That's question number 2. Okay, question number 3. I don't think I can ask this question. This question is mixing the idea of GFS with transaction, like optimistic concurrency control. And so because I'm not going to talk about optimistic concurrency control, but this is actually a very interesting question. It's essentially applying the principle of concurrency control, the principle of two-phase locking, try to enforce the Google file system to have a stronger consistency criteria, because Google has this consistent or define this type of property. And then we're talking about, okay, if you apply, if you don't care about performance, slow down by this kind of concurrency control protocol, the traditional one, then what will happen over here? Okay, so this is, if you're interested, we can talk about that, but right now I want to focus on all the questions that's related to, okay, this one is actually I haven't covered. I'm not sure I will cover. If you're interested in this topic, I can talk about that, is talk about peer-to-peer system. Peer-to-peer system, there is what we call structured peer-to-peer or unstructured peer-to-peer. In the structural peer-to-peer, there is a system, there is a concept called DHT. DHT stands for distributed hash table. So essentially all the important, in fact, I would say all the peer-to-peer service we're developing today, if you want to scale, you have to be structured peer-to-peer system, meaning that you have to use some kind of distributed hash table in order to support that. Okay, just tell you that this is there's a one very earlier developed DHT peer-to-peer system. It's called Core. Core is a particular way of designing DHT, distributed hash table. The idea of a peer-to-peer system was really popular in the maybe before 2010. So at that time, let me tell you that technology always go like this. You have something which is under some kind of control, and people want to break the control. People develop something called peer-to-peer, and then we want to control again. We go back to things like AWS or Google Cloud. If you think about what peer-to-peer is doing, is that it probably started with late 90s, but 2000 to 2010 probably it's a major period, is that we actually have our own computer. That means I have my laptop, I have my network bandwidth, I have my memory space, and everybody have that connect. And then how do we actually aggregate all this computing resources get connected on the internet? And how do we actually be able to organize and then perform some kind of computation for sharing music? BitTorrent is one of the major ones. That's actually peer-to-peer system. Okay, so, and then you can see that when this concept get developed, people realize that, well, instead of for us to actually contribute, why don't we just outsource everything to a company like Amazon Web Service? And they actually host all the things together. Instead of doing peer-to-peer, your computer, my computer, they're actually connecting with cluster of computer with much higher speed. So therefore, because of the on and off period, because they're pretty much managed by somebody 24/7, instead of you only use your computer sporadically. So the design is actually going to be quite different. But this is the concept. I mean, my conjecture is that the concept of decentralization peer-to-peer will come back one day. After people use so much about the cloud, eventually people realize, oh, okay, it seems to me I have a lot of IoT device at home. I want to do something. And that's actually going to this kind of paradigm. So computer science is kind of sad. We have like the same technology. We have a mainframe, and then we have personal computer, then we have network of server, and then we become peer-to-peer. Now we have a cloud. You see that it's just the same idea, just repeat, all right? And yeah, the same type of problem. I mean, somebody make money. Other than that, I don't see it. There's that. All right. Anyway, I shouldn't be too negative about that. All right. This question. Okay, this is again related to Hadoop, which is related to the cloud-based file system. I would talk about map and reduce at that time. This is essentially the cloud-based system that today we're all based on the map and reduce. If you're interested, I can spend a lot of time on map and reduce. So you don't have to worry about this question as well. Okay, I'm going to go to the next exam. What happened? Okay. What did I do in 2016? I sometimes forgot what I asked. Anyway, all right. Oh, this question I like. This question is, I always talk about social operating system, how does operating system managing social resources? And this question I cannot ask because I didn't talk about the social network yet. All right, I will talk about social network. That's why the social centric operating system was actually trying to cover some of this topic. But this is essentially saying that I try to motivate students to develop a appreciation application such that when you actually realize somebody is very stressful and I turn out to be the person to causing that stressful. For example, it could be you're very stressful and who is responsible for that? You're an instructor of ecs251. I either assigned something or did something or didn't do something. cause you stressful? And how do we actually be able to let computer provide us a reminder to be sensitive to that issue? So that was a design about a social file system. I mean, we're looking at the sensor. So the signal you can see is if somebody, there's a sensor, lightning sensor, and then you just trigger it 57 times within an hour. That is a clear indication that this person might be up to something. Okay, so just that was a one question I feel very interesting to ask the student to develop that. Let me see what this question is about. Oh, this that particular example, I'm really proud of myself. This is another example. I asked the student to look at. I was actually talking about search engine recommendation system that time. So about that's part of the social kernel. Yeah, I remember that quarter I spent a lot of time on social kernel. That's why. So I actually asked the student to say, well, if you have somebody doing carpooling. So typically people carpooling, they will talk about something, but then you want to see that what kind of article you will recommend them to read during their breakfast. And then what would, so they can actually talk about those articles. So that was actually one type of scenario. The second type of scenario is that we all actually want to fly out from Sacramento Airport, San Francisco Airport. We're going to take a 7-hour flight to somewhere else. And the thing is that you're actually going to be sitting next to two strangers. And what kind of things you will be reading so you can actually communicate better. So that's actually the idea. But the core issue is actually about privacy, because if you're actually going out carpooling, usually you know those people already. So then you can actually probably do that. I actually took it back. At that time, we don't have Uber. Today, probably you can have Uber and Lyft. You can actually sit together with a few strangers. And that is also the idea. But then when you take an airplane, most likely the people who sit right next to you are actually you never met before. So under that kind of system, how do we actually recommend? Okay, so anyway, I feel that that's a good question for students to think about what they should design a system to work on this case. But anyway, you don't have to worry about that. You'll worry about something like this, but in the context of those 6 papers. Okay. I think that's the only question I asked that quarter. Oh, lucky then. I didn't ask any knowledge question. They don't have to remember anything. Okay, fine. All right, let's look at what I asked spring 2011. I include this because I think there was at least one question. Okay, background FSCK, you don't need to worry about that. This is sub update, you don't need to worry about that. Sub update, you don't need to worry about that. You don't need to worry. Why are you going to include this one? This one is concurrency control. You don't have to worry about that. Okay, this one. Oh, this is distributed. Yeah, okay. This is the same question. Okay, I include this one because only this question is actually the same question as I showed you earlier. So that's why, you know, if I'm going to ask you a question, I'm going to ask you this type of question with a higher probability for the knowledge, because I think that is something which every student should know when they learned about two-phase commit. Okay, so that's why I include it, because it's important. And actually it's the same thing with transaction support. Okay, I'm actually, wait a minute, this 3 questions are the same? Did I ask the same question? Oh, I'm shame on me. All right, I shouldn't do that. All right, no more. So I asked the question in 2 years. Okay, that's fine. In 2 years, I'm okay with that. All right. What? So let me actually pick it up. What was this? Why this one doesn't work? Let me go for the next one and then I'll come back. Go to the final exam. For spring 2007. No, I'm not, I won't ask you distributed I know. I should have in the first part. I'm actually talking about I know, but look at distributed I know. Design of distributed I know. Wow, this is the exam I made. everything about extended inode to do distributed inode. Do I have a question, different question at the end? No, this is all about inode. Yeah, this one I know why I included, because I was okay. I can just be honest with you. I didn't ask this question. I won't ask this question tomorrow. Oh, sorry, Thursday. So the interesting part about this question is that how do I actually take the concept I know to extend it such that I can actually implement, support distributed file system like AFS differently. So that is let me see, I think I have another question about AFS. Do I have another question about AFS? Yeah, this is about, you see that I actually talk about this design for all different file systems. They all use distributed inode, and what are the security issues you need to worry about, which I didn't have time to actually focus on that. So that particular project, I remember I spent a lot of effort in understanding the security issue related to distributed file system. And therefore, I have this DI, DDI, FDI, those kind of different kind of extended concept of inode. I mean, just want to share with you, I think it's a benefit for you. The concept inode is very simple, but inode can be extended to actually do a lot of different things. If you actually, in your design issue, you will see that inode is an enabler. It's an architecture enabler. But when you actually apply to different concepts, you can actually fit into the concept, change the idea, and then you can actually have a different way of building your information system that way. Okay, I am now curious about what I did for that midterm, 2007, is that right? 2007, let me actually go to 2007 folder. This is a midterm. 2007 midterm. Okay, I must include the wrong thing. Sorry. This is a snapshot. This is FSCK. Okay, so this is the question I could have asked. So I basically asked that what are the main differences between NFS, AFS, and GFS? Compare the three things. So if I'm going to answer this question, I will first compare NFS and AFS, because NFS is a stateless design and AFS is a stateful design. So meaning that when I deal with this, I have a different way to handle server and client crashes in the scenario. So that is a main difference between NFS and AFS. They actually design. And the second part between GFS and AFS and NFS, then we see the main difference is that in the GFS, I separate the control about the directory and the SS block, finally. And in both NFS and AFS, the directory structure is actually being distributed itself among all the machines. So NFS, for example, you have one machine, you actually need to go to the other machine in order to get access to the directory tree. And then you might have to go another place to actually access the directory. So in fact, in NFS, sometimes the control about your directory tree is not as coherent, not as centralized as GFS, Google File System. That's actually the first part. The second part is about the commit protocol, or is about the different copy, replica of the file system. In AFS, you actually could potentially have a multi-version AFS. It means that you have a different version about what's going on. But in by default, AFS and NFS, I think when some of the server are unavailable, then your application are typically more sensitive to those failure, and you might or might not be able to proceed. But with GFS, the design is to be robust and such that every copy you have 3 replica. And particularly the way, I might not actually say this in class, but the way they actually typically, how do they arrange the 3 replica? The way they arrange is that 2 of the replica is usually on the same rack. And then there's a 1 replica, they're actually putting a different rack or even in a remote location, and such that it's more robust against different kind of failure. Okay, so that's the difference between NFS, AFS, GFS. And of course, you can see I asked another question, which is also similar. I said, what is the main difference between 2-phase commit and 3-phase commit? Why the difference is something important to have, which is really the same question I asked about that blocking condition of 2-phase commit. That's 3-phase commit is basically the design to handle that particular condition that's going to have put everybody into wait state. Okay. Okay. Transaction, you don't have to worry about that. Okay, this is actually something you need to see how you can explain that. Is why pcsp avoids deadlock. So basically, you have to. Okay, let me actually tell you how I will answer that question. The way PCP avoids deadlock, I thought I have a solution for this one. I have to see if I can dig it out. The reason it will avoid deadlock is because it actually enforces the locking sequence will be corresponding to the priority level, according to the priority ceiling. Because of priority ceiling, you actually be able to force the locking according to their priority level or the priority they are receiving. So essentially, what's happening is that any deadlock must actually have a circular dependency. When you have a circular dependency, that means the okay, I actually use a board. No, I don't want to use a board because remote student cannot see. I will describe it. If you think about that, any deadlock, you must have a circular dependency. And if any of the circular dependency represent a propagation of priority ceiling value. If you think about that, if I have a circle, the smaller circle is 2 semaphore or 2 lock. Each of the lock must have a priority ceiling value, right? Must have a priority ceiling value. So essentially, we're saying that there's only 3 cases. In fact, there's only 2 cases. One case is this 2 semaphore, their ceiling value are the same. Or this 2 semaphore, their ceiling value, one is bigger than the other. Okay, so in order for, if you think about that, let's actually think about the easy case. They are actually ceiling value are the same. These 2 are ceiling value are the same. So in order for this to happen, it must be one thread is going to lock one resources waiting for the other, and the other thread is lock the other semaphores waiting for this. This is called circular dependency. That's called deadlock. But according to priority ceiling value, if there is a lock semaphore, which my priority is not even greater than, equal is not good enough. Remember, I emphasize, always have to be greater. if my priority is not greater than, I cannot even lock the second one. So that's why when this two, if you form a deadlock, if their priority ceiling value are exactly the same, you cannot have a circular dependency because of the priority ceiling protocol. Does that make sense? Okay, if you don't understand, I can repeat it. Okay, that's actually a harder argument to present. Okay, so now we're actually looking at the bigger one and the smaller one. Okay, so one ceiling value, the bigger, one ceiling value, the smaller. If the semaphore with a higher ceiling value, means high priority, get locked first, then essentially the second semaphore cannot be locked. Because the ceiling value is low, represent the highest priority thread can lock the lower ceiling value semaphore, is not going to be higher than the higher one. So if the higher get locked first, the lower one cannot actually do anything. Okay, so now let's actually go the other way. If the lower priority ceiling semaphore get locked first, okay, assuming this one is a lower semaphore, this is a higher semaphore. Okay, that one is available, but this one I already lock it. Right? So now you have somebody with a higher priority is coming here to lock this one. He actually locked this one. Okay, he actually locked this one. And now he tried to lock this one and realize that this one is already being locked, right? So then that's actually going to have a deadlock because I actually want to lock this one, that. But think about that case. Well, what could that happen? If I actually want to lock this one, and if I want to lock the lower priority, so the ceiling value of this semaphore must be the same or higher than my priority. So if this one is a lower priority, is already being locked, I actually cannot lock this one. This is a higher priority because this ceiling value must be already at least equal to mine if I want to lock it. So in this case, there is a contradiction. So the argument is usually we present these three different cases. They're the same, bigger, smaller, and you realize that in either of the case, we're going to have a contradiction. And therefore, you cannot have a deadlock in the priority ceiling protocol. Yeah. Yeah.
Contradiction in
The last one? Okay. So let me actually use this slide, okay? No, I've just used Microsoft, using this one. So assuming I have M1 and M2, M1 and M2 are, let me use S1. Semaphore 1 or semaphore 2. You know what? I should use MU. Mutual exclusion 1, mutual exclusion 2. Okay. So in order for this to be deadlocked, it must be thread X, which is thread X locked, MU1, and thread Y locked, MU2, right? This must be the case, then I will have that. But furthermore, I know that thread Y want to lock, wait for MU1, while thread X is actually wait for MU2, right? That's a way how we can have a deadlock. Okay. So first, we should know that both, let's actually look at priority ceiling value. So priority ceiling value, priority ceiling of MU1 must be greater than the max value of priority for TY and TX, right? So my priority must be greater than, the ceiling value must be greater than this two. And similarly, it's the same for MU2. So both of their ceiling value has to be greater. Okay, so now we're actually assuming that we're assuming, the other one that we're assuming the case, which is, now let's actually look at the case. PC MU1 is actually greater than PC MU2, okay? Just say one is greater than the other. Now I'm, remember, there's two cases probably the same way, okay? Which one is bigger? It's the same way. I'm going to make an argument over here.
Professor?
Okay, so I have this. So now I'm going to proceed with argument. Okay, so if I actually be able to, now I'm actually coming here. If I actually can lock this one, if I can actually lock this one, MU1, assuming this happened first, okay, sorry, this happened first. And I'm actually argue, can you even lock this one? You probably cannot, right? You cannot lock this one because why? Let's actually say if this one get locked, you cannot lock this one because right now MU1 is being locked, and I know the PC value of MU1 is greater than the higher priority of TY and TX, right? So therefore, you're in you're TY, and your priority cannot be even bigger than PCMU1 or PCMU2. In fact, sorry, PCMU1, because you tried to lock MU2. And so therefore, you will fail this test. You will fail this test because you cannot. So in other words, we can never reach the circular dependency because one of these two must be locked first. When one of them get locked, the other one just simply cannot lock because of this condition. If you have a circular dependency. So this one is circular dependency of two, just two semaphore, but you can extend the generalized to multiple semaphore. Yeah. That's why it guaranteed avoid deadlock because of the rule. Okay. Yeah, it's a bit tricky. Even for me, I have to reorganize my thought. I believe it like a religion. Oh, this must work. But then every time student asks me a question, I have to reconstruct, say, oh, why I believe that? Yeah, okay, fine. All right. Any other question? Yes. Oh, you said this one? Yeah, sorry, this one must be greater than equal. Yeah. The seeing value, yes, is greater than equal. But when we decide whether we can lock, that's actually be strictly, so that's why it's very important. It has to be strictly greater than, yeah. Otherwise it won't work. I personally, the proof, this way to prove is probably easier than the paper. I remember I read that paper a long time ago. It's when they prove is greater than, sometimes the proof is pretty hard to follow, at least for me. Yeah, but you can use this kind of counter argument to argue that. Yeah. Okay. Any other question for this one? Okay, we're done for this batch, so I'm going to go over. Yeah, please.
If you lock everyone first, then shouldn't the second condition fail the first one when we try to lock it?
Yes, yes. So according to a PCP, you actually cannot they cannot lock they cannot lock this one. Okay, but I do want to say this. Let me bring my PCP slides. I might not even have to set it correctly when I present this protocol. Let me go to the PCP one. Okay, when I do, hold on. When I do this slide, when I explain that, okay, thread number 2, when they actually decide to lock a available mutual exclusion on the right, on the left, sorry, they must actually check for all the currently locked semaphore. I should add 3 words by other threads. So in other words, if you yourself already locked the semaphore, you don't need to worry about that. You don't need to worry about that. So it will be exclude your own. If you already locked, that's okay. So that's why in this particular exam question, once you lock, no, not this one. Once you lock the MU1, you can actually lock MU2 because you already lock MU1. It's you lock MU1, so it's okay. So that has to be clarified. Yeah. Okay, good. Any other question from remote? Oh, there is a 10 message. Let me actually check. Yes. Shuhaya, yeah, you're right. Yeah, it's a PC is a priority ceiling. Okay, good. All right, any other question for this one? Okay, let's shift to something else. You know what, I better, yeah, this one's probably okay. Just one question. Let me go to my another announcement. Okay, here. Okay, let me actually. Okay, this is I know, don't worry about that. This is copy on right, don't worry about that. FSCK, nope, this one is full cover. Return 2015, what did I do? Yeah, this is about, yeah, this is about file system, so don't worry about that. This is I know, what's this? This is YouTube. Okay, fine. Nothing I need to worry about. Let me close it. No, this is all file system. Vino, I won't ask Vino. Self-update journaling, no. Director, I know. It's fine. Yeah, there's nothing for this one. Okay, this one. 2016 final exam. 2016 is probably the last time I actually taught ECS 251. Okay, this is the exam. I mentioned to you that both questions are basically a free spirit question. Let me see, 2016 midterm, what did I ask? Yeah, this is about I know, yeah. I thought this, why I feel this is the same. Okay, 2013 final. I thought we already covered this earlier today. I probably already sent you this last time, and then we covered it today. Yeah, this is about optimistic concurrency control, two-phase locking. That's what a two-phase commit. About what is the condition we have to wait. This is, yeah, I already covered this last time. What's this one? Yeah, this is about the HT question. And this is our map reduce. Yeah, that's it. That's pretty much, I try to find all the exam I have in the past, whatever, how many years. I have probably some even earlier, but I don't think I'm going to cover that. Okay. All right, any question? From remote?
Yeah, I have a question.
Okay, so what I think we should end it here. And 4 o'clock, if you are want to participate and just log into the channel. Tomorrow also 4 o'clock. Okay, we can do that. So let's take care of the midterm this week, and then starting next week, we can spend time to talk about some more advanced topic and also talk about some of the coding part for homework assignment number 2, 3, as well as for the final project. Okay. Yes. Oh, you said the reference implementation. Okay, I haven't released it. I will release it soon. All right, thank you for your reminder. I forgot about that.